The cosmos is a vast, dynamic system, a swirling ballet of celestial bodies held captive by an omnipresent force. Planets, moons, and countless asteroids navigate through this immense void. Despite the seemingly endless opportunities for collision, the solar system maintains a profound, long-term stability. This equilibrium is not accidental, nor is it purely a consequence of gravitational attraction. It is maintained by a phenomenon known as orbital resonance. At its core, orbital mechanics dictate the paths of all celestial objects. Gravity, the fundamental force, dictates that objects with mass exert an attractive pull on one another. This pull keeps planets orbiting stars and moons orbiting planets, tracing elliptical trajectories through the vacuum of space. Without additional stabilizing mechanisms, the cumulative gravitational perturbations might lead to chaotic instability over eons. The precise dance of planets around the Sun follows predictable mathematical rules, first codified by Johannes Kepler. Each body possesses a distinct orbital period, the time it takes to complete one revolution. These periods are not random. They are intrinsically linked to the body's average distance from its gravitational primary. Yet simple gravitational interaction alone cannot fully explain the observed order. For extended periods, the solar system has exhibited remarkable order. The planets do not spiral into the Sun, nor do they fling themselves into interstellar space. This stability is largely attributed to specific synchronized relationships between the orbital periods of certain celestial bodies. These relationships, where orbital periods are simple integer ratios, define the concept of orbital resonance. Consider Jupiter, the largest planet in the solar system. Its immense mass exerts significant gravitational influence, shaping the orbits of smaller bodies and even distant planets. This gravitational shaping is not always disruptive. Under specific conditions, it can synchronize the motions of multiple objects, locking them into stable, repeating patterns. These synchronized patterns prevent chaotic interactions. When two orbiting bodies have periods that are exact integer ratios, for example, one body completing 2 orbits for every 1 orbit of another, or 3 orbits for every 2, they are said to be in resonance. This periodic alignment means that their gravitational interactions occur at the same points in their orbits, reinforcing or canceling out perturbations in a consistent manner. This predictable interaction stabilizes the system. A classic example of orbital resonance is found within Jupiter's Galilean moons, Io, Europa, and Ganymede. Their orbital periods are locked in a 1:2:4 ratio. For every 1 orbit of Ganymede, Europa completes 2 and Io completes 4. This precise synchronization ensures that their gravitational pulls align predictably, preventing chaotic divergence and maintaining their stable dance around Jupiter. This rhythmic gravitational tugging has profound effects beyond mere orbital stability. In the case of Io, the continuous flexing caused by the resonance generates immense internal heat. This heat manifests as the most volcanically active body in the solar system, with plumes of sulfur and silicate materials erupting constantly. The internal energy is a direct consequence of the resonant interaction. Beyond the major moons, orbital resonances also shape the asteroid belt between Mars and Jupiter. The Kirkwood gaps, observed as regions largely devoid of asteroids, are a direct consequence of mean motion resonances with Jupiter. Asteroids attempting to orbit in these resonant zones are repeatedly perturbed by Jupiter's gravity, eventually being ejected from those stable paths. Conversely, some asteroid families are stabilized by resonance. The Trojan asteroids, for instance, are trapped in Jupiter's L4 and L5 Lagrangian points, 60 degrees ahead and behind the planet in its orbit. These regions are naturally stable due to a 1-to-1 resonance with Jupiter, preventing the asteroids from straying into the giant planet's path or being ejected. The Kuiper Belt, a vast disk of icy bodies beyond Neptune, also exhibits the powerful influence of orbital resonance. Pluto, along with other Plutinos, is in a 2-3 mean motion resonance with Neptune. This means that for every 3 orbits Neptune completes around the Sun, Pluto completes 2. This resonance protects Pluto from close encounters with Neptune, maintaining its long-term stability. This intricate system of gravitational interactions and resonant locks is not unique to our solar system. Exoplanetary systems, increasingly discovered with advanced telescopes, also demonstrate evidence of resonant configurations. Planetary systems often evolve towards such stable states. minimizing disruptive interactions over billions of years. It is a fundamental principle of celestial mechanics. The precise conditions required for a stable orbital resonance involve not just the ratio of periods, but also the eccentricities and inclinations of the orbits. Subtle gravitational nudges over vast stretches of cosmic time can either reinforce or disrupt these delicate balances. Understanding these dynamics is crucial for predicting the long-term evolution of any planetary system. Without the stabilizing influence of orbital resonance, the solar system's architecture would be far less predictable. Over immense spans of cosmic time, the cumulative gravitational interactions between planets could induce chaotic behavior, potentially leading to planetary ejections or collisions. The vacuum of space, devoid of friction, provides no damping mechanism for these chaotic excursions. The sheer scale of cosmic time necessitates such intricate stabilization. Human engineering projects, even those designed for centuries, pale in comparison to the billions of years over which planetary systems evolve. Orbital resonance provides a natural, self-organizing mechanism that ensures system longevity far beyond any terrestrial construct, a testament to the universe's inherent order. The precision required for resonance is extraordinary. Even slight deviations from the exact integer ratios of orbital periods can disrupt the delicate balance. A non-resonant system subjected to continuous, uncoordinated gravitational perturbations would eventually succumb to increasing orbital eccentricity and instability. This contrasts sharply with the robust, synchronized movements observed in resonant configurations. Consider the celestial mechanics as a grand clockwork. In a non-resonant system, the gears might grind and eventually fail as their teeth misalign. In a resonant system, the gears are perfectly synchronized, each turn of one precisely corresponding to turns of others, allowing for frictionless, enduring operation. This mathematical harmony underpins the observed stability. Certain types of resonance can even be self-correcting. If a body slightly deviates from its resonant period, the gravitational forces acting upon it can gently nudge it back into the stable resonant configuration. This inherent feedback loop helps to maintain the long-term integrity of the synchronized orbits, a powerful mechanism against chaotic drift. The stability offered by orbital resonance is particularly critical in the unforgiving vacuum of space, where there are no atmospheric effects or other dampening forces to absorb errant energy. Without these precise gravitational ballets, the relentless cumulative effect of even minor gravitational nudges would inevitably lead to systemic breakdown over astronomical timescales. Thus, the presence of orbital resonance transforms a potentially chaotic gravitational field into a highly structured, enduring system. It is a fundamental process by which the universe maintains its grand order, ensuring the continued predictable movement of celestial bodies within our solar system and beyond, against the backdrop of immense cosmic forces. Comparing the solar system's stability to terrestrial systems reveals the profound differences in scale and fundamental physics. On Earth, friction and atmospheric resistance constantly damp motion, bringing objects to rest. In space, the near-perfect vacuum means that once set in motion, objects continue indefinitely unless acted upon by another force, primarily gravity. This absence of damping makes orbital stability exceptionally challenging. Terrestrial engineering often involves materials that degrade or break down over relatively short timescales, measured in decades or centuries. Space architecture, conversely, must endure for millennia, operating within extremes of temperature and radiation. The natural self-correcting mechanisms of orbital resonance provide a durability unmatched by any human-designed system. Consider the precision of a high-end mechanical clock versus the cosmic clockwork of the solar system. A finely tuned clock can maintain accuracy for years, but eventually requires maintenance. The orbital resonances, however, have kept the planetary clock of our solar system ticking with incredible precision for billions of years, without external intervention or repair, a testament to cosmic engineering. The sheer emptiness of space also means that gravitational influences propagate without hindrance. Unlike sound waves or atmospheric pressure, which diminish rapidly over distance on Earth, gravity's reach is infinite, its strength decreasing predictably with the square of the distance. This long-range interaction allows for the subtle, yet powerful, synchronizing forces of resonance to operate across vast interplanetary distances. On Earth, Ecosystems are driven by energy flows and biochemical cycles. In space, celestial systems are governed by the elegant, immutable laws of physics, particularly gravitation and inertia. Orbital resonance is a prime example of these laws manifesting as a self-organizing principle, transforming potential chaos into enduring predictable motion. It is a cosmic dance of unseen forces. The stability provided by orbital resonance is a vital precondition for the very existence of habitable zones over long geological periods. Without this celestial ballet, planetary orbits could become too eccentric, leading to drastic temperature swings unsuitable for the development of complex life. The steady rhythm of resonant orbits provides a consistent environment for evolution to unfold. Despite their inherent stability, orbital resonances are not immutable. They can collapse or evolve under specific circumstances. The slow, cumulative effect of non-resonant gravitational perturbations from other distant objects, or the loss of mass from one of the resonant bodies over astronomical timescales, can gradually nudge a system out of its delicate balance. One potential mechanism for resonance collapse involves the gradual evolution of a system's central star. As stars age, they undergo changes in mass through processes like stellar winds or, eventually, catastrophic events like supernova explosions. Such mass changes alter the gravitational potential well, subtly shifting orbital periods and potentially disrupting previously stable resonant configurations. The long-term influence of galactic tides, the gravitational pull from the Milky Way's vast stellar disk, also introduces minute perturbations. While these forces are incredibly weak over human timescales, over billions of years, they contribute to the slow, relentless drift that can challenge the precise conditions required for perfect resonance, gradually pushing orbits out of sync. Close encounters with rogue celestial objects, such as interstellar asteroids, comets, or even other stars passing through the solar neighborhood, represent more abrupt threats. A sufficiently massive intruder could gravitationally slingshot through a system, imparting significant energy and momentum, drastically altering established orbits and shattering resonant locks. Planetary migration, particularly during the early chaotic stages of solar system formation, provides evidence of past resonance formation and subsequent evolution. Giant planets, through gravitational interactions with protoplanetary disks, can migrate inward or outward, sweeping smaller bodies into and out of resonance. This dynamic process sculpts the final architecture of a planetary system. The very stability provided by resonance can sometimes lead to instability under different conditions. For instance, specific types of resonance, especially those involving small integer ratios, can amplify gravitational nudges, leading to highly eccentric orbits that could result in collisions or ejections, depending on the specific configuration and initial conditions. Over eons, the cumulative effect of these myriad subtle and abrupt perturbations means that no resonant system is truly eternal. The universe is a place of constant, albeit often slow, change. The precise clockwork stability of orbital resonance is a temporary state, though one that can persist for timescales far exceeding human comprehension or terrestrial geological epochs. Understanding these mechanisms of collapse is vital for predicting the ultimate fate of planetary systems, including our own. While our solar system currently exhibits robust resonant stability, the long-term future, over hundreds of billions of years, will inevitably see the slow unraveling of these intricate gravitational ballets as stellar evolution and galactic dynamics exert their influence. The existence of orbital resonance highlights the universe's capacity for both order and chaos. It demonstrates that stability is often a dynamic equilibrium maintained through continuous, precise interactions rather than static perfection. This ongoing dance dictates the enduring structure of celestial architecture. The vast, silent expanse of space is often perceived as a realm of cold indifference, yet within it, an intricate web of physical laws orchestrates a cosmic ballet of profound order. Orbital resonance, a testament to the elegant mathematics of the universe, stands as a cornerstone of this enduring stability. It permits planets and moons to trace their paths for eons, fostering environments where life can potentially emerge and flourish. This intricate celestial mechanism underscores the interconnectedness of all bodies within a gravitational system. No object exists in isolation. Its motion is perpetually influenced by the subtle, yet powerful tug of its neighbors. Resonance transforms these individual interactions into a collective, synchronized rhythm, preventing chaotic drift and maintaining systemic integrity. For humanity, dwelling on a planet whose very existence has been safeguarded by these cosmic harmonies, the study of orbital resonance offers a profound lesson. It reveals the universe as a self-regulating entity, where fundamental forces conspire to create stable, long-lived structures far grander and more complex than any human construction. From the fiery volcanoes of Io to the distant icy realm of Pluto, the fingerprints of orbital resonance are etched across our solar system. These resonant relationships are not static but dynamic, a continuous negotiation between gravitational pulls, maintaining balance against the backdrop of an ever-changing cosmos. They are the unseen threads weaving the fabric of cosmic order. The long-term stability provided by orbital resonance is not merely an academic curiosity. It is a fundamental precondition for the persistence of habitable conditions. A stable planetary environment, shielded from catastrophic orbital shifts, allows for the gradual evolution of complex life over billions of years, making these cosmic symmetries crucial to our own existence. As we continue to explore the cosmos, discovering new exoplanetary systems, we invariably search for similar signs of stability. The principles of orbital resonance provide a framework for understanding not just our own celestial neighborhood, but potentially countless others across the galaxy. What other subtle, self-organizing principles might the universe employ to maintain its grand, enduring structure?